If you leave a warm cup of coffee in a cold room, something very predictable happens. It cools down, until eventually it settles and doesn't change any further. If we were to measure how warm our coffee was over time, we'd probably see a graph like this. The warmth decreases, then stays constant. It doesn't keep cooling down, and it never spontaneously heats back up. Now this already raises some important questions like, why isn't this process reversible, and why can't the coffee just stay warm? Over the course of this series, we are going to answer these questions, but before we can explain why this happens, we need to be much more precise about what is happening. Because right now, all we're really saying is that the coffee feels warm or cold. But what does that mean? Is warmth something we can measure? Something that belongs to the coffee itself? Or is it just a sensation we experience? And if it is something real, how do we know it's consistent? How do you know that what feels warm to you is the same as what feels warm to someone else? So before we explain why systems like this change, we need to answer a simpler, more fundamental question. That is, what is temperature? It turns out that there are actually three main approaches to defining what temperature is. The thermodynamics version, the statistical physics version involving particles, and also the entropy version, which is more advanced. In this video, we are going to discuss the first approach, which is by far the simplest and is essential before even attempting the others. We are going to show that temperature is a real, measurable property of everything around you, and do so without talking about atoms or molecules. To do this, we're going to take everyday observations like this one, and turn them into something precise. We will define what it really means for systems that stop changing, a state known as thermal equilibrium, and from that, build a definition of temperature that has nothing to do with human perception. In doing so, we'll uncover the Zeroth Law of Thermodynamics, which is foundational for all the other laws. By the end, temperature will be something we can measure consistently, no matter who or what is doing the measuring. So let's start with a simple observation. Instead of the coffee example, let's take two solid objects, say blocks of iron. One feels warm and the other feels cold. If we bring them into contact, something very predictable happens. The warmer block cools down and the cooler block warms up. This continues for a short while until eventually nothing changes any further. This is just like what we saw with the coffee in its surroundings. So before we try and define what this warm or cold feeling is, we can at least say that it always seems to settle over time. If we left these two blocks alone, completely undisturbed, they would simply remain like this. We have a special name for this state, thermal equilibrium. The word thermal comes from the ancient Greek term thermos, and it just means warmth. Equilibrium is just a fancy term for a state of balance. So before moving further, let's be precise about what we mean here. When we say two objects, or more generally, two systems, are in thermal equilibrium, we don't mean they just feel the same to us. Instead, we're describing what happens when we bring them into contact. If we bring two systems together, and one warms up while the other cools down, then clearly something is changing. But if we leave them long enough, we reach a point where neither system warms up or cools down any further. Now the systems are in thermal equilibrium. So what decides this? Why do some pairs of systems change while others are already settled? There must be something about the objects themselves that determines this. This must be independent of whether we interact with them ourselves to feel how warm they are. We have a name for this something, temperature. If the two systems aren't in equilibrium, we say their temperatures are different. And if nothing happens, we say they are equal. But there is still one hole in our story. We don't know that temperature is consistent. Sure, in our minds, we can think of a warmth scale, i.e., some things feel warmer than others. But how can we show that temperature is a measurable scale like this? Well, it's actually very simple. We just need more than two objects. We just need a third reference point that allows us to measure the temperature of the first two objects without bringing them into contact. If we bring the third object into contact with the first, we will see them go to thermal equilibrium. Imagine now we brought the third object toward the second object, and nothing changed. That would mean they are in thermal equilibrium also. So the third object is now in thermal equilibrium with the first object and the second. This means that the first object must also be in equilibrium with the second. This might seem like a small detail, but we have been able to do something very important here. We can say that first and second objects have the same temperature without even bringing them into contact. This might seem ridiculously obvious, but this ensures that temperature can be compared in a consistent way. This statement is also known as the Zeroth Law of Thermodynamics. Now, I'm aware this still feels a bit vague and technical. After all, how do we even know whether the two systems are in thermal equilibrium without doing it by feel, which is obviously not reliable? Well, for this, we actually need a little more physics first. It turns out that there are quite a few things in nature that directly correlate with temperature. A thermometer is basically anything that responds to temperature in a clearly visible way. The most common kind is a liquid metal, mercury, in a tube. In warmer environments, the mercury expands, and in colder environments, it contracts. This is something we can observe with the naked eye. So if we used a thermometer as our first system in our example, we could bring it to the first object, watch the mercury expand until it settles and stops expanding further. We could then bring the thermometer to the second object, and if the mercury doesn't change, we know that the first and second objects are in thermal equilibrium and therefore the same temperature. We can also turn temperature into a precise number scale. Over the last few centuries, there have been several attempts to do this. First, Fahrenheit decided that the lowest temperature was the freezing point of salt water. Later, Celsius set 0 degrees to the freezing point of water and 100 degrees to the boiling point of water. Finally, 100 years later, Lord Kelvin realized that if you extrapolate how gases behave, there is a lowest possible temperature at around minus 273 degrees Celsius. He used this to define absolute zero. All of these scales are still used to this day in different circumstances. By the way, if you're enjoying this video, check out the Decipher Physics app and websites, which have interactive lessons and practice questions for this video and others. It's completely free to use. So let's make clear what we've learnt in this video. Firstly, we've seen that systems evolve toward thermal equilibrium in nature. Thermal equilibrium occurs when two systems remain settled. Their level of warmth doesn't change further. We then made a proper description of what this warmth is. Instead of just being something we feel, it is a property belonging to the materials themselves. We call this property temperature. If two objects are in thermal equilibrium, they have the same temperature. We then showed, using the Zeroth Law of Thermodynamics, that temperature is a consistent quantity throughout the universe. We can compare the temperature of one object to another without having to bring them into contact. Finally, we gave a brief overview of how we can use this practically ourselves, such as measuring how much mercury expands as a measure of temperature, and introducing a few temperature scales that have been made. But there are still many questions for what is actually going on here. Firstly, what is actually happening when we bring hot and cold objects close to each other? What is happening as they reach equilibrium? Clearly, something is flowing between the objects which we haven't yet explored. In the next video, we're going to introduce a new type of energy specific to temperature. We call this type of energy heat. Thanks for watching.